Okay, welcome everyone again to the third day of talks in astronomical observational techniques and instrumentation. Today promises to be at least one of the top 3 days of talks so far that we've had. And I'd like to introduce the first speaker, Victoria Butler, who's going to talk to us about water absorption in stars. She's from Rochester Institute of Technology.
Professor. So as you mentioned, my name is Victoria Butler, and I'm going to be talking about water absorption in stars. So let's get into it. The first thing that we need to talk about, obviously, is water. So here's what we're going to talk about: categorizing water transitions, the effect of temperature on water, because temperature is obviously going to behave differently on Earth than it does in a star, so that's rather important. Finding stellar spectra so that we can actually analyze the water absorption in the stars, analyzing it, and then let's see what our results look like. Water is very, very complicated, at least more complicated than other things like just basic hydrogen. They're polyatomic, which means they're going to have vibrational, rotational, and electronic transitions from their degrees of freedom. But fortunately for us, those are going to lie in the spectrum in the ultraviolet, infrared, and microwave, which are useful because we do have observational resources in those areas. So here's why it's kind of complicated. You're not going to cooperate, right? There it goes. So it's complicated because of all of the degrees of freedom. We've got a symmetric stretch, we've got an axisymmetric stretch, bends, and then you get these things called libration, which is where the orientation between the atoms isn't really changing, but the molecule itself is physically rotating in space in some way. And this is actually caused by dipole moments in the water. So because of all of these different movements that are possible for the water molecule, we have lots and lots and lots of transitions. So this is what it looks like in Earth's atmosphere. This is the amount of transition that you get in our atmosphere from water. And so as you can see, over in the mid-infrared here between like 4 and 10, it's almost completely non-transmissive in our atmosphere, which means there's a lot of water in those regions. So when we look at stellar spectra later, we're going to try to focus on this particular region to look for our water features, assuming that we can find them in those regions in a star. We're going to talk about that in a little bit. So here's kind of a different way of viewing it besides a graph. This is just a table showing you where you might expect to see the infrared vibrational absorption spectrum of liquid water. 2 keywords there, vibrational and liquid. Both of those things could be variable for our star. We might expect that we're going to find everything in the gas phase and not necessarily the liquid phase. And we might also expect that we're not just going to have vibrational spectrum, but also other things. So, for example, you can see for the 6 micron line, you get a bend, which causes that particular feature. Some of the others, you get libration. So some of the features that I'm going to be focusing on later in my stellar spectra are going to be around this 6.08 micron. It's actually going to be at 6.3 microns, which I'll explain later. And we're also going to be looking at another feature which doesn't happen to appear in this table, but which is caused by a different process. So this is a graph made by an individual whose research is literally to compile line lists of all of the different places in the spectrum where you would expect to find water, which, as you can imagine, borders over 2,500 different lines over our entire spectral range. That's a lot. So that's why, in one respect, we're concentrating on a very small area of the spectrum. So as you can see here, the green line, this is wavelength on the bottom, which is in microns. And then up here, this is just absorption coefficient. And so you can see right around the 6.3, that's this tiny little feature right here. Doesn't bode too well for us for later because it means it's probably going to be harder to observe in our stellar spectra. But we have this huge, awesome feature right around 10 microns, which is going to be very visible, hopefully, in later spectra. And so this is actually, the green line is for gas phase water, blue is ice, and then red is for liquid. And one of the interesting things to note is how the liquid and the ice are relatively around the same region of the spectrum, but when you get to the gas phase, it changes quite a lot. So the trick to analyzing our stellar spectra later is going to be not restricting ourselves to thinking of just one of these types of phases, but trying to include all of the different ones to see. We might not necessarily just have gas phase water, but also some of the others as well. So we're just going to try to keep ourselves mindful of the fact that there might be other features out there. So we've talked about categorizing the water transitions. Now comes the difficult part, is translating that from kind of the earthly version of water to the stellar version of water. So my initial attempt at this, I thought that this was going to be very straightforward and not in the very least hard. I was very wrong. So this is what I tried to do. I tried to think about it in terms of the binding energy of a water molecule and said, okay, this is literally all of the amount of energy it would take to break this molecule apart and to disassociate it. And at that point, we would no longer find water absorption features in the star. So then I said, okay, what are the forces that exist in the star that you would need in order to break apart that binding energy? Next, actually calculate that for different types of stars, so different temperatures, different pressures, different sizes. All of that comes into effect. What combination of those causes it to break apart? So you might have a star that's relatively small, dwarf size, but has an immense amount of pressure, or it could be a neutron star, versus something that's much, much larger, like a red supergiant. They're going to behave very differently in those situations. And then, what's the limit where water is no longer present? Can we actually detect a threshold, a combination of those different factors, which keeps us from being able to detect it? And for which spectral types do those different temperatures and pressures correspond to at that limit? Well, the problem is that we don't know as much as we think we know about the interiors of stars, and especially not about the photospheres. I guess we know a little bit more about the photosphere because it's easier to get spectra of rather than of the interior of the stars. But there's a lot of processes, a lot of processes that can affect any kind of atom or molecule. I mean, that's what a star is. It just messes with atoms and molecules all day. That's its job. So it's very difficult to figure out what factors go into this. Also, water has many methods of decomposition. It doesn't necessarily just break apart into H and O and O, or that's wrong, H and H and O. There we go. It could break down into H2 and then OH if the temperature increased just slightly. If the temperature increased even more, it might then break apart into even more constituents. So here's kind of what I mean. This is a model of a mole fraction you might find in a system at 1 atmosphere, but at very high temperatures. We don't know what the pressure might necessarily be in a star. It could be very high, or it could be around 1 atmosphere in the stellar photosphere. So this is just kind of a rough model. But as you can see, this can break apart into H2, OH, O2, and then constituents of just hydrogen and oxygen. So those all might be factors in a star. You might just find hydrogen, you might just find oxygen, and maybe there was a potential for water, but maybe the system wasn't quite right for it to be able to be formed or present. And lastly, you can make a baby model of how gas should behave as an ideal gas. For example, when they were looking at the mole fraction here, that's if you think of the ideal gas law, where you had that coefficient N in it. That's kind of the value you're looking at when you look at the mole fraction, at least in some form. But that's very, very hard to do if you don't have an ideal gas situation. And figuring out whether or not the photospheres of stars actually are an ideal gas is kind of an important factor to figure out. So anyway, it's very, very hard, and I wasn't physically able to come up with an answer that I was happy with. However, fortunately, some other people have looked at this problem before, and actually they've spent most of their adult lives looking at this particular problem. This is what they actually did, which is much more complicated than what I was doing. They tried to solve for the motions of the individual electrons instead of just the atoms themselves. They've got potential energy surface, solving for the motion of the nuclei, energies and wave functions, thermodynamic properties, and then way down here we have include physical conditions in the star, like temperature and pressure, etc. So all of this combined is what they used to calculate line lists and to make a graph like this one, which shows a temperature dependence on the water absorption coefficient for water. This was compiled using a database called HitTran, which is basically just a database devoted to categorizing the line transitions for different molecules and elements and atoms. And in this particular case, they took that and said, okay, maybe we can make this specific for just stellar photospheres and see what we can get. And in this particular case, they developed a model which they call BT2. They take those line lists and they say, all right, we're going to use this in a star now. And this is what they found. So if you look at it, the colors correspond to different temperatures, and the wavelength is on the bottom, and then the absorption coefficient's on the top. We can see sort of the same features that we saw in one of our other pictures. So over here you can see the huge 10 micron feature, the tiny little 6.3, and then right over at 4 microns you can see another interesting looking feature. One of the most important things about this graph that taught me sort of what's going on in the system is that no matter what temperature we're looking at here, at least within this range, the placement of the feature hasn't moved. The amount of water that we're seeing at each of those points has changed. The absorption coefficient's changed, but the physical location of where that is found in the spectra has not moved. So that's kind of comforting in a way, because when we're looking at stellar spectra later, we're going to be trying to look for it in the same place in each star, because that's what this model at least has told us, is that that hasn't varied. There are some caveats to this. For example, this graph does not change with pressure. So depending on whether that system in the star has changed or not, we might find that there are differences in, for example, if you guys remember from chemistry where your triple point is for your molecule, that might change depending on how high of a pressure that you go. So this is just kind of a baby model, but it's the best one I can find thus far. And they actually went one step further and said, based on this model, we can sort of predict what you should be able to find in different types of stars. So in our particular case, I'm going to be looking at K stars and M dwarfs, and also an S-type star that I was lucky enough to find in the database. So the M dwarf has a temperature range between 2,000 and 3,700, which kind of falls into the region of the last graph that we showed. And it says that you should expect to find that it's oxygen-rich and has H2O in it. Same thing as you go down your C stars. As you get down into cooler and cooler objects, you're finding more and more instances of polyatomic atoms. And conversely, if you go up to higher temperatures, you're finding that there's only really diatomics. So this is our basic model for saying we expect cooler stars are going to have more water absorption in them at different temperatures. So the next problem is now we actually have to analyze our stellar spectra. And this is where life became very, very difficult for quite a while. So the first thing that I attempted to do was to go to Simbad and say, I would like to find all of the different types of M stars that I can possibly find in your database, take that RA index list, throw it into another database, and just see if I get any hits on it, to see if you have any of these as spectra. And so what I tried at first was GR15, which was the Apogee survey, which I was very excited about because they do have a lot of really well-resolved features in their data, except I couldn't find it for the 300 RA index that I tried. So I moved on. The next thing I thought about was, oh hey, there's all of these ground-based telescopes. That's not going to fly because our atmosphere has all of the water features that I'm looking at in the stellar photospheres, and it completely absorbs those features when looking through it in the infrared. So it's basically not transmissive at all for our telescopes in that region for water. Next thing I tried to look at was MAST. I think, given more time, this would have been a really good resource because they have a lot of great, really high-resolution spectra in there. However, unfortunately, I couldn't get the FITS files to actually work in IDL. It kept saying you have an empty file, there's nothing there, I don't know what to do with it. But in the future, I would really like to try to find some other databases to work with. And many other attempts, you get the idea. Basically, I hit gold when I found IRTS. Problem being, this was launched back in 1995. Not necessarily a problem, but it's a very old database, which means our data might be slightly less polished because the technology back then wasn't as refined as it is today. So this is what it looked like. It's actually really tiny. It has a 15-centimeter aperture. You could probably hold this in the palm of your hand, or palm of both of your hands if you really wanted to. It was launched by an H2 rocket and then captured by the NASA Space Shuttle, cryogenically cooled with liquid helium. And then over here is kind of a diagram. This is the side view. What we're going to be using for our spectra is the mid-infrared spectrograph. It's also got a near-infrared and a far-infrared. And it also has this star sensor so that it can actually pinpoint a star to look at and say, okay, take that data. Also has these secondary and primary mirrors in here. So the light comes in, bounces off the primary, goes back into the secondary, and then goes back into split off into one of these devices, depending on which one you'd like to look at. So just a basic on that. Here's some of the attributes for it. The thing I found really cool about this was the overall size of this thing. They measured in millimeters cubed. So just think of how tiny that is. I mean, I wish they'd put like a banana or a penny or something next to the images so you can see like how tiny it was. But it's really amazing how small these instruments were back then. They used a silicon photodetector. I was told that Aerojet Electrosystems isn't a company anymore. So that's also a thing? No.
They've been bought like 3 times.
Really?
So, yeah, I think Boeing bought them.
RCA Electronics. You guys are 90s kids, so you know the tapes are like usually made by RCA. Also, look at the data rate is in bits per second. So the amount of data that they're collecting isn't really great. So all of this is probably making me slightly pensive about what our data is going to look like at this point, and believe me, I was slightly. Anyways, I'm looking at the mid-infrared point source catalog for this device because the near-infrared point source catalog didn't have a way for you to filter out your objects in any significant way. It just gave you a big .dat file and said, pick things out of this. And I said, wow, that's really difficult because you have like 16 columns and over like 3,000 data points. So I stuck with the Mears catalog because it was a lot nicer, but their telescope actually did 2 different scans. One is a south scan, one is a north scan. And when I went to go collect my data, I said, they let you choose what piece of the sky you wanted to take the data from, and I said, all of it. So that's what we're gonna look at next. This is what it looks like when you go to get the data off of their website. This is all of the data, and you can click on these and it'll show you a nice pretty picture of the spectrum and a lot of other information that goes with it. Some of the things to note in particular are A, which stands for the position accuracy. So that's really important for me because if I'm looking up this star in another database, like Simbad, but it doesn't have really good position accuracy, I might not necessarily find it in the position I'm searching it for in the other database. So we want to pick one that has a very good position accuracy so we can be sure it's the same one that we're looking at in the database. The next thing to note is the quality of the 4 bands that they took data in. They classified that by this quality over here. Anytime you see a 3, it means that's the highest quality they could get for that band. If you see anything lower than that, you're kind of getting into iffy territory, whether or not your data is usable or not. Further things to note are this thing called C. They designed their, well, it says number of, oh, no, spectral classification. They designed their own spectral classification system for this particular data set. So the first thing I had to do was actually learn what each of those letters meant before I clicked on anything and tried to analyze it that may or may not be a star. So here we go. Let's click on it, see what happens. Astronomer's version of poking it with a stick. This is what the very first entry looked like in the database. As you can see, the error bars essentially could make it potentially a straight line. So, needless to say, I was a little bit concerned at this point as to what was going to happen with this project. However, we're going to roll with it because this is what we've got. So, moving along. This is what I tried to do. I took the RA index for the first object, I popped it into Simbad, and I said, okay, can you tell me what the spectra of this star is? Because even after I looked at the spectral classification, it didn't tell me what the specific spectral type, like M star, S star, A star was. It just said it's either a star or not a star. So this happened a couple of times, more than a couple, more like a few hundred times. So we did this for a bunch of different ones, and I got 17 spectra out of the database that I could confirm with Simbad. This was what their classification system was, so I could narrow down my search a little bit. Group A is what I'm focusing on. It says it has color temperatures of 2000 Kelvin, which is around the M star, so that was perfect. That's what I was looking for. Red giants with little or no circumstellar envelopes. That's really, really important because the circumstellar envelope has potentially water sources in it, and we don't want to look at the envelope, we want to look at the star itself. So we want to get rid of all those other sources. So this one had an envelope, don't like that. This one, not sure what the source is. This one, very extended objects, probably not stars, and these ones can't even be confirmed as a celestial object. So literally everything else except for A, we're going to be ignoring. So now we need to get down to analyzing stellar spectra. We're going to be using equivalent width as a measurement for our absorption features. Because in my particular mind, considering the low resolution of the data and the amount of error that we have in it, it's going to be a lot easier than trying to do any other analysis method that I can think of right now. So basically, that's the equation I used in IDL to calculate it. This is just sort of a definition of measuring what the equivalent width is equal to. And so let's give it a try and see what happens. So this is just an example measurement of one of the stars. This is one of the very good ones that I found where the error bars were not off the scale of the graph. So what I'm looking at right now, I've plotted these vertical dotted lines to kind of show you where we expect to find the absorption features. And then this red line overplotted is a fitted Gaussian that I used, because I said stars generally kind of sort of look like a black body. Gaussians can kind of sort of fit a black body relatively well. And so I said, for this particular type of star, I'm going to try to fit that Gaussian to the black body to try to find my continuum. And so I'm using that fitted Gaussian as the continuum level for the level at which you would find no absorption feature if it was there. You would just see the black body line. So in this case, I'm looking at the 7 micron line, which I'll prove to you later why that's an important line to look at. This line is, of course, again, the Gaussian. There's the absorption feature. Right away, we can see a little bit of a problem with analyzing the spectra because my 2 data points on either side are above the continuum line. I got some negative numbers for it. So basically, I had to go in and kind of manually wrestle with it and tell it just ignore that, just keep doing it anyway. So yeah, the fact that we don't have a continuous line is slightly problematic. And if I did this in the future, what I would really like to do is find one of the more sophisticated equivalent with measuring programs out there, and I know they exist. Kevin told me of one of them that I tried to use. I tried to find one from Cloudy, which involves uploading a line list file, which I really wasn't sure how to do. So given more time, I'd really like to try to go back and redo this in a more efficient way. But for the cut and dry case here, this is the best we could do. So this is what the K spectral types look like that I could find. Basically, I'm just going to run through each type and tell you what things I noticed, what things I didn't notice. So for this one, can you guys actually see the vertical dotted lines on any of these? Is it a little fuzzy? Okay. Turn the volume down a little bit more. Or not, that's fine. So basically, there's one right over here, which isn't useful in any of our graphs because it's right where the data cuts off. So it's not really, thank you. You're not really able to determine much from it. We've got the 6.3 micron over here, and then the 10, and I think there's a 7 right in there too. So what you can kind of see, there really isn't any kind of discernible absorption feature. You might be able to find something over here at 10 microns. I did measure it, but I'm not very confident whether or not it exists. This one definitely didn't really show any kind of water feature at all, which is what I was expecting. So I'm expecting most of these K-stars are going to have very weak absorption features, if at all. And that's kind of what we found. So this is an M4. We skipped ahead from M1, 2, and 3 because I couldn't actually find any of those in the database, so we're going to M4. So what we can see here in this first one is that there kind of looks like something at 10 microns, maybe, kind of, sort of. You look over at these other ones, kind of looks like it's empty again. Maybe you have something at 10 microns, who knows. And then in this one, yeah, kind of not really definitive. The 10 definitely looks like it has a deeper feature than the surrounding area, but again, the error bars kind of make it almost pointless. Going on to M5, I don't know, 7 starts to appear, which hasn't really happened before. I don't know why I included this bottom one because it's kind of a mess. What I looked at before, everything after starting at 10 microns and above has a lot of error in it. And my best guess is that's probably due to some kind of instrumental noise in the data because it's consistent through every single spectrum that I looked at. So literally everything after the 10 micron feature is kind of unreliable because it's got very big error. But we're going to try anyway, just because we're stubborn. So here's a 10 micron feature in M6. Kind of a little feature here. Can't really see anything in the 6.3 anymore either. Looking down here, sorta. Yeah, 10 might be there. 10's definitely there in that one. 7, still no 6. Keep going. I don't know, maybe you see something. 7 is still here. The kind of interesting thing is that you're going along in these, and you're kind of thinking, nothing's really getting bigger, nothing's really getting broader, there's not a lot happening. You would expect it to be a little bit more obvious, I suppose. This one is where it started to get interesting, because you could definitely see a feature over here at the 7 micron. And probably you could see something at 10 if you really, really wanted to. So, but interestingly enough, I hardly ever saw a 6.3 micron line. I think I only measured two 6.3 micron lines in all of the 17 spectra that I analyzed. This is the last one for M star. This was really weird because when you got up to this high, like 8 and 9 M types, you started to see these huge gouges out in the 8 micron line. And I'm still not entirely sure what that is. I think it shows it in one of the other later plots by another group that I have. But it also showed these features here, here and this feature here, which are all really close to the absorption feature wavelengths that I want, but just exactly offset from where they're supposed to be. So maybe there's some redshift going on in there, I'm not entirely sure. But it definitely seemed consistent across all of these different types for that to happen with the later types. Particularly for the S-type star, which is a very cool, relatively small star, even more so than an M star. So this is the kind of star where we would expect to see the most amount of water absorption. So we look here, yeah, there kind of sort of might be a 10 micron. Something might be happening over here. Who knows what's going on with the 6.3 micron line. There's some weird stuff going on over here. So now we need to talk about what we actually found. Firstly, let's use our eyes because in a way, absorption features are really kind of an eyeballing it method. Even when you measure the equivalent width of your line, it's still very subjective to where you pick your endpoints to be, what you pick your continuum as, very much up to the interpretation of the user. So let's use our eyes. This is the cooler type star that we expect to see absorption features in, and this is the warmer K star that we really don't expect to see a lot of anything in. They're both on the same scale, so that's kind of helpful. This one, as we said before, can't really see much of anything. This one you could probably see a 10 micron feature, and you could probably see a feature over here if you really wanted to. So roughly speaking, we can say there's probably more absorption features in this star for water than in a K star, just roughly speaking. Here's what the actual numbers ended up being for the equivalent widths. So on the bottom and top, spectral type K through S, and the equivalent widths measured for each one. You can see kind of a rise going up towards M6, and then it kind of drops back down again as you go further and further, which is not at all what I expected to see. But again, the spectra is really noisy, the errors are very big, and the equivalent width measurements are not very solid. So as far as the effectiveness of using this result for any kind of determination, rather poor. But I would say that it follows along with what we saw observationally, that the M6 stars seem to have a lot more water absorption in them than at least their counterparts like K stars. So that at least we can say. Something else interesting, the 7 micron line was consistently had a higher equivalent width than the 10 micron line, which might be due to certain properties of how that transition is created from the water molecule. So it might be caused by rotational or vibrational or electronic transitions, and each one might be a little bit different, and that can change how much of each one you would expect to see in the star. So for the 7 micron line, we're seeing more maybe because that kind of transition is more common in stars than the other one is. This is what other people found because they didn't use as much of my spectrum, which starts here and goes to the right, which is the mid-infrared. They use more of the near-infrared from this same database. And they found actually quite a lot of water absorption in these stars. They only identified one line in mine, which is at the 7 micron level, that they could identify. And what we were looking at before, that huge jump, they say is caused by silicates. So that could be part of why that data is so massive over on that end. But as you look up, this starts with hotter stars and proceeds down to cooler stars until you get to about D. E and F are different. They're not from the same kind of stellar spectrum we were looking at. So if you look at it, as you go down, you can see that these absorption lines are definitely getting deeper. This one just plows right down into the ground at the 4 micron level. And then these two are definitely identified. Even 10 micron is jumping up because of the silicates, but that might be for that particular type of star. This D is actually an M8 or 9. So that particular star has something in it that obscures my water feature. So this is what they found, which is good because it's consistent with what we thought. Cooler stars have more water absorption. The temperature does affect the amount of water absorption in the star. Things that I might change in order to get that result in the future. Improve the equivalent width measurements so that they're more accurate. I can get a better trend of what it looks like for each of the features. Be more picky about which stars that I choose, because it really does matter whether it's a dwarf or a supergiant. And the one thing I didn't do when I picked my different stars was confirm that each of these are relatively the same size. And that seems very important to me. So that might be why we didn't see a very consistent trend in the absorption. Many spectra showed a lot of promising features, but it couldn't be confirmed what spectral type they were in SIMBAD. So I need to find a database that has much more readily identifiable spectra. and just get a larger set of data, because you can't really get a lot of results from 17 stars. You really need a bigger catalog to identify and get a better average value for your equivalent width at different stars. So that's pretty much it. And also a really big thank you to Crystal Tyler, because she helped a lot with trying to find data and actually get the equivalent width measurements to work out. So that is all. Thank you.
Okay, time for questions.
So you only used objects that had a Sinbad reference, right? So the one that you said that there could be a possible redshift for, did you like calculate it just for fun, or did you see how distant that object says it is in Sinbad?
I didn't go back and double check, mostly because when I went back and looked at this graph, some of these looked like they had the same kind of offset, at least a little bit to me. But it's definitely something that I would like to try in the future. I assumed that because it was from the same database that it probably was corrected similarly to all the others. I would find it very strange if that one star wasn't corrected for redshift. But it's definitely something to consider. Because all of my other features ended up where they were supposed to be based on the paper that I looked at, I assumed that it probably wasn't caused by redshift. But it's a good point. I would like to look at that.
Did you look at the photometry of the objects that, like, do you have any pictures or images?
Images of the objects. I know that they were in Sinbad, but I didn't actually physically look at them. Is there something about the images that would have been helpful? Are you thinking like whether they're dwarf or a supergiant kind of?
Well, I'm just wondering how alone they are, I guess. I don't know how to say that right, but basically because like silicate features are a dust feature.
Mm-hmm.
So if you're having a lot, and that's usually around 10 microns.
Okay.
You get that. So
right.
If you have a lot of like, because you were saying that you got a lot of like of your stars had those like 10 micron features.
Right.
So I'm wondering if it's like there's a lot of dust around that star, and that's what's mixing up with your
Right.
spectra.
Yeah, it's definitely a really important consideration for looking at water in these stars. Mostly I was hoping that I wouldn't find that because I looked at the spectral class A, which said there were almost no circumstellar envelopes,
Yeah.
but that doesn't mean there's nothing. So it's probably a good point that those particular ones might have that feature around them. In the future, I want to be more picky about what stars I choose because it's very important. Any other questions?
So I had a few questions. I think you had a plot that showed gas phase water and
Yep.
liquid and ice, I think.
Mm-hmm.
Maybe it was around 6 or. Oh, maybe it was it.
I think it's one of the previous ones. This one?
Okay, yeah. So in the upper two, is that ice and liquid?
Correct.
Are those emission lines?
They say that all of them are absorption features.
Okay, so the continuum is much higher than the highest peak
Yes.
for the ice and the liquid, right?
Right. They said that,
Big chunks taken out.
correct. They said that they developed a synthetic spectrum for pure H2O, and then added in the line list from HRAM to see what it would do to that spectrum. They didn't necessarily make it look like a black body like our star, which is why I included the temperature dependence graph. But it was useful because it gave me a starting point of looking at where I might find those features. When I read the paper that did an analysis initially on these types of stars, they only identified a 7 micron line. And I wondered why they excluded some of the other transitions of water that you might find in stellar. And so that's why I was very interested in 10 micron and 6.3, because it seemed like in some of those cases you could find those features there.
Can you go to the other one? I think it's 3 or 4 slides down. The other one that shows the spectrum.
This one.
Yeah. Do you see a shift in the sort of centroid of the absorption peak as a function of temperature?
I guess for some of them, yes, I do see that. For this one here and here, and this one too, it seems like the 10 micron doesn't show much of a shift, but that is an important point. That's probably why I was a little more loose in my measurement of some of the lines because I noted that maybe there was a slight shift depending on temperature and pressure.
Why does it shift?
My assumption is that the temperature changes the energy transitions for the molecule. Because if these are caused by, instead of rotational but more vibrational electronic transitions, the temperature would have a big effect on where that transition would occur based on the energy of the system and the molecule. That's my best guess. Something that would definitely be nice to confirm. The paper didn't look at a lot. They were more concerned with getting the actual physical line lists to model for a star. They didn't spend a lot of time modeling any other temperatures rather than this.
So I assume that the temperature would relate to the collisional probabilities of populating higher energy states.
Very true, yep.
So with the higher temperature, there are more collisions that populate the higher states that put more of the systems in higher states.
Mm-hmm.
That means that the lower energy states are less
Less
populated.
Mhm.
Yeah, I don't know if that's related to the centroid, but.
It wasn't shifted too much, and since I was looking at a very narrow range of temperature for the M stars, it wasn't too concerning. If I was to look at multiple other spectra, I would probably be a lot more worried.
And did you look at ISO SWS?
Not that I'm aware of, no.
Okay, because they looked at, I'm not that familiar with the data sets, but I know they looked at red giants and supergiants because ISO was relatively less sensitive, just like this other mission, which is good for your project because
Right.
less sensitive means that you don't can only look at bright things.
Mm.
And red giants and supergiants are bright,
Right.
right? So ISO was the same way, more sensitive than this, but still not really that great. So I know that they looked at red giants and red supergiants. I did a quick search. There was a paper, water absorption in red giants and supergiants.
Right.
So you want to look at that.
Mhm.
And I think it covered 2.4 to 40 microns. 2.4 to 40 microns.
Mhm.
They were focused, I think, on the 6 micron
Okay.
features, which I think you were looking at.
Yeah.
Also.
That was a lot of the difficulty with this particular project because if you look at this, most people were focused on M dwarfs and not M supergiants, which I found really difficult because obviously they're going to have very different types of features. So that's another consideration is that maybe what I was